Okay, so maybe we should get started. So our second talk this morning is by Moreau, and you can see your title here, Nilpotent Slodowy Slices and W-algebras. Please go ahead.
Okay, so thank you very much for the invitation. It's a great honor for me to speak in this conference. So in this talk, I would like to explain how to use geometry of nilpotent Slodowy slices, which are quite standard object in representation theory, to study some interesting problems on W-algebras emerging from the recent 4D to D duality in physics. And this is a joint work with Tomoyuki Arakawa and Yesro Van Ekeren. So let me first recall some general facts on vertex algebras and their associated varieties. So first, I recall that the vertex operators algebras is a vector space, complex vector space, equipped with a linear map from V to the vector space of Laurent polynomial series with value on V, and satisfying a number of axioms. So in particular, we have the important fact that we recover the vector A by applying the corresponding field to the vacuum vectors and taking the limit as 0. So this is the so-called state field correspondence. And we have also the important locality axioms, which say that to any fields commute up to some power of Z minus W. And here, this axiom is equivalent to the knowledge of OPEs. So here I am using the physicist notation, which gives the singular part of the product AZ-BW. And in fact, the knowledge of these OPEs is equivalent to the knowledge of all commutation relations between the modes AN and BM. All right, so this is roughly the definition of vertex algebra. And to get vertex operators algebras, it is also required that V is positively graded with finite dimensional graded components. And also, there is a distinguished vectors, the conformal vectors, whose associated field, the stress tensor, usually denoted like this, is such that the A-lanes here appearing in the coefficients here satisfy the Virasoro relations. And here C is an important invariant called the central charge. All right, so now to such algebraic structure, we can attach in a canonical way a certain variety, algebraic variety, as follows. So more precisely, we have contravariant functor from the set of VOA to the set of affine Poisson varieties. So I denote by XV the corresponding varieties, which is defined as follows. It is a reduced scheme associated with some Poisson algebra RV called the Zooc2 algebra, which is defined as follows. So how is defined RV? So first of all, by the state field correspondence, you can write V as a vector space generated by this normally ordered product of fields. And then you consider the subspace of V generated by all these elements for which N1 and so on plus NR is greater than 1. And then, so in other words, C2V is a vector space generated by the vectors of this form, A minus 2B. And now RV is just a quotient of V by this vector subspace. And it is naturally a Poisson algebra whose algebra structure is given by taking the image of the normally product. And the Poisson structure is an image of A0P. So in terms of field, you can express the Poisson algebra structure like this. All right, and then, as I said, the associated variety is a corresponding reduced scheme. Maybe I should note here that RV is not reduced in general, but in this talk, I consider the corresponding reduced variety. All right, so the object we get here, XV, is an important invariant of the vertex algebras, which captures important properties of the vertex algebras. So it's important to study vertex algebra themselves, but it's also important because it appears in a recent conjecture on the Higgs branch of higher dimensional conformal field theories. So this is what I want to mention now. Okay, so recently, a group of physicists, so Beam, Lemos, Liendo, Ehlers, Rastelli, and Van Ries, constructed a remarkable map from the set of 4D n is equal to 2 superconformal field theories to the set of 2D conformal field theories, so that is to say the set of VOAs. And these maps enjoys nice properties. The idea is that some invariance of the 4D theories has to be reflected as invariant of the vertex algebra side. So in particular, this map is such that the Schur index, which is a certain invariant of the 4-dimensional theory, is equal to the normalized character of the corresponding vertex algebras. So here, the normalized character that I denote chi v of q appears in the previous talk. So it's a trace of v graded by the action of L0. And there is a shift by C over 24, where CV is the central charge. And Q is, as in the previous talk, exponential 2i pi tau, where tau runs through the Poincaré half plane. All right, and there are other required properties. But let me just make some remarks about this map. So first of all, this map is supposed to be injective in the sense that two different theories should give different non-isomorphic vertex algebras. However, it's far from being surjective. Actually, the vertex algebras appearing in this correspondence are never unitary, and the reason is that the 4-dimensional central charge is related to the 4-dimensional central charge as follows. And for the 4-dimensional side, the central charge is always assumed to be positive. And so you see that the 2-dimensional central charge is always non-negative. It's always non-negative. So in particular, it is not unitary. And actually, we will see that the vertex algebras appearing in this correspondence are quite exotic. So this is what I want to explain now. So there is another important invariant attached to any 4-dimensional conformal field theories, which is called the Higgs branch. And there is a conjecture by Beam and Rastelli, which are part of this group of physicists, which says that the Higgs branch of any such theory should be equal to the associated variety of the corresponding vertex algebra. So this is very interesting because this will give a mathematical definition of this Higgs branch. So this conjecture has been proven by Arakawa in the special case of the classes theory, which is a distinguished theory of 4-dimensional superconformal field theory. And here he was able to prove, because there is a mathematical definition of the Higgs branch in this case, which was obtained by Braverman, Frenkel, and Nakajima. So except for these special cases, the conjecture is fairly open. And another remark is that the Higgs branch is usually a hyperkähler cone, so possibly singular. So I mean by that the smooth part has a hyperkähler structure, while by construction, our associated variety is merely a Poisson variety. So no need to be hyperkähler in the smooth part. So this means that this conjecture suggests that vertex algebras appearing in this correspondence are very special. So actually, it is expected by physicists that the Higgs branch has only finitely many symplectic leaves. And so this means that this is also the case for the associated varieties of the corresponding vertex algebras. So a vertex algebra is called quasi-Lis if the corresponding associated variety has finitely many symplectic leaves. And it is called Lis if xv is just a point. So of course, Lis vertex algebras are quasi-Lis. And the conjecture suggests that vertex algebras appearing in the 4D, 2D duality are quasi-Lis. So this class of vertex algebra is very rich, and I would like to give some examples and also non-examples. Okay, so I would like to give examples and non-examples in the context of affine vertex algebras. So let's consider G hat, the affine Kac-Moody algebra associated with the simple Lie algebra G, and then consider the following induced modules. So here GT acts trivially on the one-dimension, CK is a one-dimensional representation of GT plus CK, and K acts as K times identity. So it is well known that this G hat module has a vertex algebra structure, and the OPEs are given as follows. And in fact, here the OPEs are equivalent to the commutation relations in G hat. All right, so here, okay, and VKG is very important for the representation theory of G hat because we have a correspondence between a VKG module and a smooth G hat module of level K. All right, so what is the associated variety here? Here it's not difficult to show that in fact, the associated variety is just the dual of G equipped with his Kirillov constant Souriau-Poisson structure. And using the killing form, we can identify with G. So this one is not quasi-Lis because here the symplectic leaves are just a co-adjoint or adjoint orbits. So we have infinitely many of them. So to get interesting quasi-Lis affine vertex algebra, let's consider the unique simple quotient of VKG. So here, it's difficult in general to compute the corresponding associated variety, but what we can say is that it is a G-invariant and conical, it's a G-invariant closed conical subset of G star. Okay, so it's difficult to compute in general, but for some family of examples, we are able to describe it. Oh, sorry. No, sorry, I thought there is a question in the chat, but it's just Reimundo. Sorry. So let's give now example of where we can compute X LKG. Okay, so first of all, when LKG is integrable as a G hat representation, then the associated variety is just 0. And this is well known to be the fact that it is integrable, it's well known to be equivalent to the fact that K is a non-negative integer. And actually the converse is true. So here we have exactly the case where LKG is Lis vertex algebra. All right, so let's now consider a bigger family of examples. So first of all, we can easily observe that LKG is quasi-Lis if and only if the corresponding associated variety is contained in the nilpotent cone of G. So it's well known that this has a finitely many adjoint orbit, and the converse is also true. So now we discuss the case of integrable G hat representation, but there is a much larger class of G hat representation called admissible G hat representation. So the definition is purely combinatorial. It was given by Katz and Wakimoto, but conjecturally, they correspond to those representations whose characters satisfy the modular invariance properties. So I don't want to give a precise definition here. So let me just say that LKG, which is actually a highest weight representation, irreducible representation of G hat, is admissible if and only if K is a rational number of this form. It is of the form minus HH, the dual Coxeter number, plus P over Q, where PQ are co-prime, and P is assumed to be greater than HH if Q is co-prime with the lassity and greater than H otherwise. So the lassity is just 1 for the type AD, 2 for B, C, and F4, and 3 for G2. So in the talk, I will mostly consider example in type ADE, so you can just take the first line for definition. And in this case, it was proven by Arakawa that if LKG is admissible, then the associated variety is the closure of some nilpotent orbit in G. And the nilpotent orbit depends on K, and actually only on Q. So this is very interesting because the closure of this nilpotent orbit has only finitely many nilpotent orbits. And also it's, you can observe that in this case, it's irreducible. All right. So, okay, so in particular, LKG is quasi-Lys if K is admissible, but this is not the only example. So I would like to give another family of example which is not admissible. So here I consider the Deligne exceptional series. So this is a series, a series of simple Lie algebras embedded as follows. So which contains in particular all exceptional Lie algebras. And I take for the level K this rational number, minus HH over 6 minus 1. And then with Arakawa, we proved some years ago that the associated variety here is precisely the minimal nilpotent orbit of the corresponding simple Lie algebra. So this is another example because you can observe that for the simple Lie algebras that I drawn in red, so D4, E6, E7, E8, the level is not admissible. So our motivation originally came from applications to representation theory, but it turns out, oh, sorry, yeah, it's just what I'm saying. It turns out that these simple affine vertex algebras for non-admissible level are precisely the vertex operators algebras that appears in the paper by Beam, Rastelis, and collaborators as a main example of corresponding vertex algebras. And actually here, it was possible to compute the Hitch branch of the corresponding theory T, and our result with Arakawa proves the conjecture in this fact. So now this result was reproved by Arakawa in the more general setting, but this was the first family of example considered by this physicist. All right. So now I would like to consider the compatibility with this associated variety with the Drinfeld-Sokolov reduction. So, okay, so I take a nilpotent element in G, and then I consider the corresponding universal W-algebras associated with G and F at level K. So, which is obtained by the quantized Drinfeld-Sokolov reduction, or if you prefer, it is described as a zeros cohomology of a B-heuristic cohomology associated with F. So I denoted the DSF in this talk. All right. And here, it's a result of Dessol and Katz that the associated variety is what we call the Slodowy slice at F. So this is a transversal slice to the nilpotent orbit of F in G. So this is just an affine space. So here F is a nilpotent element fixed, and GE is a centralizer. Maybe sorry, I didn't explain, but F can be embedded into an SL2 triple, and GE is a centralizer of the positive part of this SL2 triple in G. So now, by a result of Arakawa, we have a description of the associated variety of the Drinfeld-Sokolov reduction applied to the simple affine vertex algebra LKV. And this is just the intersection of the associated variety of LKG with this Nilpotent Slodowy slice. So as soon as you know this variety, you know the associated variety here on the left-hand side. So in particular, according to the previous family of examples, if K is admissible, the associated variety you obtain here is the intersection of a nilpotent orbit closure with with the Slodowy slice. So this gives many examples of Lie and quasi-Lie W-algebras, because as soon as here you get quasi-Lie vertex algebras, here you get also quasi-Lie vertex algebras. And in fact, here I computed the Drinfeld-Sokolov reduction of the simple affine vertex algebras, but conjecturally, this is equal to the simple quotient of the universal W algebras, provided that this one is non-zero. So, and this conjecture has been proven in many examples. All right, so now as you see, this kind of object, so intersection with nilpotent orbit closure with Slodowy slices, appears in the context of associated varieties of vertex algebras, and this is precisely what we call nilpotent Slodowy slices. So let me say a few words about these nilpotent Slodowy slices. So I just recall the definition, but as I said, if I pick a nilpotent orbit in G, it's just an intersection between the closure of this orbit with a nilpotent Slodowy slice where F is in the closure. If F is outside the closure, this intersection is just empty. So historically, these nilpotent Slodowy slices were studied because the local geometry of the nilpotent orbit closure at F is encoded in this nilpotent Slodowy slice. So it was important to understand singularities of nilpotent orbit closure. So in fact, the geometry of this object has been mainly studied in the case where GF is a minimal degeneration of the closure of O, which means that GF is a maximal orbit in the boundary. And the reason to study mostly this case is that the singular locus of the nilpotent orbit closure is just a complement of the orbit inside the closure. So people were interested in studying singularities of this, in particular normalities, so they mainly studied this case. So there are well-known examples that you probably know. So first, I recall that in the nilpotent cone, so the set of nilpotent elements of your Lie algebra, there is a distinguished nilpotent orbit called the regular nilpotent orbit, with whose closure is precisely the nilpotent cone. And then, if you take the complement, you remove this regular nilpotent orbit, there is again a distinguished nilpotent orbit, which is dense. And this is called the subregular nilpotent orbit. So now if you take for O the regular one and for F, you pick an element in the subregular nilpotent orbit, it is well known that the corresponding nilpotent Slodowy slice has a simple surface singularities at F of the same type as G, if G is simply laced. That is to say, of type AD. So this is the Bursztyn-Slodowy theory, which confirms a conjecture of Grothendieck. So this is the most famous examples. And at the extreme opposite, if you take for O the minimal nilpotent orbit, so this is a unique non-zero nilpotent orbit of minimal dimension, and you take for F 0, then the nilpotent Slodowy slice is just a closure of this minimal nilpotent orbit, and this one has a minimal singularities at 0, which is so-called a minimal symplectic singularities. And between, it is much wider. And the generic singularities has been determined by Kraft and Procesi in the classical types in the beginning of the 80s, and much more recently by Fu, Juteau, and collaborators for the exceptional types. So what I'm going to explain is how to exploit this story for some interesting problems on W-algebras. So as you see, these Nilpotent Slodowy slices appear in various areas. So as I have just explained, they appear in the theory of symplectic singularities. So this is maybe the more classical area where they appear. And as we have seen before, they appears also as associated varieties of simple W-algebras. So as I said, it is interesting to exploit geometry to study W-algebras, but conversely, we will see that some of our results can give new light on the theory of singularities on Nilpotent Slodowy slice. And also, these slice appears as Higgs branch of some four-dimensional superconformal field theories in the context of Argyres-Douglas theory. And the last two facts are connected by the Higgs branch conjecture of Bingham-Rastelli. So, so this is what I want to specify now. And then I will explain some which kind of problems we are interested in. Is it okay so far? No question? Good. Okay. Okay, so as I said, so recently some physicists, so Xi Yao, I'm sorry for the pronunciation, and Wang, observed that simple W-algebras appear as I don't know how to say, but as vertex algebras corresponding to Argyres-Douglas theory, which has distinguished classes of these 4D theories. And in fact, they mainly appear that when K is a boundary admissible, which means that K is admissible, but the numerator that I denoted by P before is as minimal as possible, which means is equal to the dual Coxeter number. And also, most of the examples appears in the simply laced case. So I assume that Q is coprime with the lacity. So this is very interesting. And now there are cases when two different W-algebras are isomorphic. So by different, I mean different G, different F, and different level K. So in particular, it may happen that a simple W-algebra is isomorphic to a simple affine vertex algebra. So which happens when F prime is just 0. And when this happens, the level K is called collapsing. So this notion goes back to Adamovich, Katz, and collaborators quite recently. And their motivation rather come from application to representation theory. But as we will see, it turns out that this notion of collapsing level is also very important for other topics. In fact, if two theories are isomorphic as physical theories, then obviously the corresponding vertex algebras are isomorphic. And then this is how such isomorphism like this may happen according to the fact that these W-algebras appears in the context of Argyres-Douglas theory. And also, if it is so, then obviously the corresponding Higgs branch are isomorphic. So this means, according to what we discussed before, we have a non-trivial isomorphism between Nilpotent Slodowy slices. Conversely, if you observe a non-trivial isomorphism between Nilpotent Slodowy slice, you can wonder whether this corresponds to an isomorphism, a kind of lifting of an isomorphism between non-trivial W-algebras. So this is what we try to study. So in order to explain our main results and application, I would like to give a more mathematical definition of collapsing levels. So, okay, I keep the notation as before. I fix an SL2 triple, as I explained, with F, and I denote by G natural the centralizer of this SL2 triple in the Lie algebra G. And it is known that this is a reductive Lie algebra. And it was proved by Katz and Wakimoto that there is a vertex algebra homomorphism from the corresponding universal vertex algebras associated with G natural into the corresponding W-algebras. So for the moment, I take the universal one. And here K natural is a certain complex number entirely determined by F and K. So in fact, it is precisely a polynomial of degree 1 in K. All right, so now the definition is the following. We say that K is collapsing if the image of the composition map, so you take this embedding and then you take the canonical projection from your W algebras to its simple quotient. So it is, the condition is that this composition map is surjective. And if it is so, one can show that this just means that the simple W algebras is isomorphic to the simple affine vertex algebras associated with G natural and K natural. So it just means that in the notation of the previous slides, I can specify what is G prime and K prime. All right. So for example, if the simple W algebras is C, then K is collapsing, obviously. So this is what we try to study. So more specifically, we try to classify all triple GFK, which leads to collapsing level, and this is a hard problem. So let me first mention some motivation. So as I said, these notions are important in the Argyras-Douglas theory. Also, so I don't give too much detail, but this notion is important in representation theory. So in fact, if K is collapsing, so as I explained, you have a vertex algebra homomorphism from this W algebras to this simple affine one. And this induces an algebra homomorphism at the level of the Zeus algebra. So the Zeus algebra is a certain associative filtered algebras corresponding to any vertex algebra, and which are very important for the representation theory of vertex algebras. So for the W algebras, what you get is the finite W algebras. So if you know, it's good. Otherwise, I don't explain in this talk. It's a kind of deformation of the enveloping algebra. And for the Zeus algebra of the simple affine vertex algebra, what you obtain is a quotient of the enveloping algebra of G natural. So anyway, if you have a collapsing level, this gives you a richer structure of the representation theory of this one, because you have this algebra homomorphism. So this is quite interesting. And the original motivation for Adamovich, Katz, and collaborators was the semi-simplicity of some categories of LKG modules in the special case where F is in the minimal nilpotent orbit. So here again, I don't give so much details, but just to say that we have various motivations. And also I would like to first collect what is known about collapsing levels. So actually, Adamovich, Katz, and collaborators obtained a full classification of collapsing level when F is in the minimal nilpotent orbit, including the super case that I'm not going to talk about in this talk. And also, together with Arakawa, we have a full classification of pairs GK where WK G with F minimal is exactly C. So this is part, of course, of the previous full classification. So the reason why the minimal case is easier is that for the minimal W algebras, OPEs are entirely known. So from that, you can guess what is a possible collapsing level. But outside this case, little or nothing was known for collapsing levels. Yeah, so as I say, the reason is that outside the minimal case, commutation relations are unknown. So the first problem is to find candidates for F and K. So here, to have some ideas is to use the geometry. So obviously, if K is collapsing, that you have an isomorphism between corresponding associated variety. And this is a very strong condition because remember that on the left-hand side, what you get is typically Nilpotent Slodowy slice. And on the right-hand side, what you get typically, it's a nilpotent orbit closure if K and K natural are admissible. So this means that you can try to find example by studying non-trivial isomorphism between nilpotent Slodowy slices. And this is what we do to start with. So to explain our main result, I would like to detail an illustrating example, which was our starting point. And this example, this starts with the question of Kreutzig and Kawasetsu. I assume here that G is SLN. And then it is well known that here the nilpotent orbit in SLN are in one-to-one correspondence with partition in N. And I denote by O lambda the corresponding nilpotent orbit. Okay, also I fix an admissible level. So here admissible just means that K is minus N plus P over Q with P greater than N. And then by Arakawa's result, the associated variety of the simple affine vertex algebra is a closure of O lambda, where lambda is a partition Q M0 S0, where M0 and S0 are obtained by doing the Euclidean division of N by Q. So this means it is a maximal rectangular partition you can include in N. Rectangular partition of length Q you can put in N. All right, and then I pick F in the closure of this, and I denote by mu the corresponding partition. And then there is a very nice Kraft-Procesi rules, removal common rows rules, which was improved recently by some mathematician, which allows to describe the corresponding nilpotent Slodowy slice. I mean by that, in some favorable cases, this nilpotent Slodowy slice is isomorphic to a simpler one. So I don't explain these rules, I explain it only on a specific example. Let's assume that N is 7, Q is 3. So here the partition is just 3, 3, 1. And I pick for M. I pick M in the partition associated with the partition 3, 1, 4. So our theory says that the associated variety of the W-algebras at simple W-algebras admissible level is this nilpotent Slodowy slice that I represent by drawing the partition. So here it is the partition 3, 3, 1, and on the right it is 3, 1, 1, 1, 1. And the Kraft-Procesi rules consist in erasing if you have common rows. So here you have only 3 in common. So I erase these two rows, and then I obtain new partition in a smaller Lie algebra. Here I obtained 3, 1 and 1, 1, 1, 1 in SL4. And this is interesting because 1, 4 correspond to the 0 nilpotent element. So this intersection is just the closure of the nilpotent orbit associated with 3, 1. And this you can interpret it as the associated variety of a simple affine vertex algebra at admissible level. So here you see from the geometry we have isomorphism between associated varieties, and one may wonder whether the corresponding vertex algebras are isomorphic. So checking some invariants such as the central charge, we obtain that the only possibilities is that P is 7 and P prime is 4. So in other words, it's boundary admissible. And the answer is yes. But of course, the geometry is far from being enough to conclude that we have an isomorphism. So actually, our method to prove it are very different. I will say a few words after. But this is how we start with. So I would like to generalize this example. And I give a explicit statement only for SLN. So our main result with Arakawa and Van Ekeren is the following. Assume that G is SLN and Q is admissible as before. And we first have a description of collapsing level in the least case. So least case is obtained when F is not only in the closure, but precisely in the nilpotent orbit. In such a case, the intersection is just a point. So here the simple W algebra is least and even rational. And okay, we have a characterization. To get collapsing level, N must be equal to plus or minus 1 mod Q or 0 mod Q. And in the first case, it's just isomorphic to C. And in the second, it's just integrable simple affine vertex algebra. And you notice that in the first cases, it's boundary admissible, and the second is not exactly. Okay, so next family of example is a natural generalization of the previous illustrating example. I pick F in the partition QM1SSS with S non-zero. And here we get this isomorphism, which generalizes the previous one. And here you notice is boundary admissible in both sides. And actually, these theorems, these results was predicted by physicists because these two vertex algebras appear as corresponding vertex algebras of the same theory, which has different realizations. All right, and we have a last family of examples, a little bit more exotic. So here N is of this form, and I pick F in this partition. And here we have also such isomorphism with boundary admissible level. And here I illustrate with the following example. I take the partition 331 as before, but this time I take for the partition corresponding to F, 322. And here the Kraft-Procesi rules leads to the nilpotent cone of SL2. All right, so this is our result for SLN, and I give you all cases because we conjecture that this gives exactly the exhaustive list of admissible collapsing levels. So we have similar results for SPN and SON, and also in the exceptional types. So of course, for the exceptional types is a case-by-case discussion. So it's interesting because in terms of associated varieties, it gives not only an isomorphism as algebraic varieties, but also as Poisson varieties. And this is not contained in the work of Kraft-Procesi, and I forgot the name of people who improved their work. But in Kraft-Procesi, just a smooth equivalence, and then it was proved later that this is actually an isomorphism of algebraic varieties, but here it's even Poisson. All right, and in the exceptional types, we feel that some non-trivial isomorphisms are actually new. Okay, and as I said, we conjecture that our results furnish the exhaustive list of admissible collapsing level. For exceptional types, up to our mistakes, it should be exhaustive. But for classical types, it's not so clear because we start with only Kraft-Procesi rules. So it may have new other examples. All right, so now I would like to say a few words about the proof. So the proof has totally different, used totally different tools. So the key point is that this is a general fact, if you have simple vertex algebras quasi-Lie of CFT types, so this means it is positively graded and the zero component is just C. So It is always the case in the examples we encountered. Then the corresponding normalized character has a nice asymptotic behavior in the sense that when tau goes through 0 through the imaginary line, that the normalized character is equivalent to this form where AV, WV, and GV are some constant. So now so here it's for any quasi-Lis, and this result was known for several classes of VOA. So first of all, it was well known for rational Lis self-dual simple VOA. So the key point of the proof that we actually extended is that here, if your vertex algebra is Lis and rational, then the vector space spanned by the finite set of irreducible V modules is invariant under the natural action of SL2Z. So using this, we can get this result. And for quasi-Lis, we don't have so strong properties, but we have a weaker statement thanks to Arakawa and Kawazetsu. It was also well known for Virasoro vertex algebras. So for example, for the universal Virasoro, we have such asymptotic behavior. And also it was known, which is interesting for us, for the simple affine vertex algebras and its Drinfeld-Sokolov reduction, where when K is principal admissible. So principal is the case where K is coprime with velocity. So, with Arakawa and Van Ekeren, we extended this to any admissible. All right. So this is one thing. And now the key technical result is the following, is that if K is an admissible level and you pick F in OK, so I remind you that this is the associated variety of LKG, then if moreover the corresponding normalized character, so on one side you take the simple affine vertex algebra corresponding to G natural, and on the other side you take the normalized character of the Drinfeld-Sokolov reduction of LKG. So if they are the same, so this means that all constants that are pairs in the previous result are the same, then K is collapsing, which means that the simple quotient is isomorphic to K natural of G natural. And the good point is that we are able to compute all these data. So we have explicit combinatorial formulas of all these constants. So it was mainly done by Katz and Wakimoto, but we extended for the general admissible level. How much time do I have?
You have about 5 or 6 minutes.
Okay, very good. Okay, so this is a key point because now using this key technical result, what is the strategy? We have, as I explained, potential candidates, and then we check. We can compute this and we check whether it's equal or not. So starting with our potential candidates, either it coincides or not, and then we draw a list in particular for the exceptional types. So I gave you some examples in the classical types. I would like to give you examples in the exceptional cases. So here nilpotent orbits are classified by the Bala-Carter theory. And then we can check all pairs of nilpotent orbits such that O is OK, and then F is in the closure. And then you take K admissibles. So for example, let's consider E6. So from the works of Juto, Fu, and so on, we have an isomorphism between these nilpotent Slodowy slices. So here I am using Bala-Carter classification. It is known that this is isomorphic to the nilpotent cone of A2, so the nilpotent cone of SL3. And our results show that this admits lifting. So we have two isomorphisms which come from this one. So as you see, the first one is for boundary levels. And this one was also predicted by physicists. And the second one is almost admissible. Okay, and similarly, we have another one. Here I use standard notation using small letter for minimal nilpotent orbits, but we have this kind of isomorphism. All right. And now I would like to give a few one in E8. So I just give you the isomorphism for between vertex algebras. So here it's interesting because here I do the converse. We start with our result, and then as a consequence, we obtained maybe new isomorphism of Poisson varieties. So we obtained this new, I say new because at least it's not contained in the literature. Probably experts in this field can recover, at least for the first one. I forgot which one is easier, but anyway, at least this gives another way to obtain this isomorphism. All right, so in the remaining time, I would like to discuss a conjecture and some other problems, related problems. Okay, so in sometimes comparing the constants, they are almost the same except for the constant A, which is called the asymptotic dimension. And in this case, most of time we can show that also K is not collapsing. WKGF is a finite extension of the simple affine vertex algebra over G natural. This is also interesting. And in most of such cases, we observe that the associated varieties are still isomorphic. But in some cases, it's not. We can show that they are different. Let's consider an example. In E6, we observe the following. So this one is not collapsing, but this W-algebras is a finite extension. And we can compute associated varieties of the left-hand side and also on the right-hand side. So here we have a Nilpotent Slodowy slices and here certain nilpotent orbits closure. And using singularities theory, we can show they are certainly not isomorphic, just because this is not isomorphic to this closure. But we can show that they are birationally equivalent. Both are irreducible, and we can show by hand it is true. So we have many examples like this, and this led us to formulate a more general conjecture that if a vertex algebra is a finite extension of a vertex subalgebra, then the associated varieties of V and W are birationally equivalent. So in particular, it implies a widely believed fact that if V is a finite extension of W and if V is least, then W is least. The converse is known to be true. Okay, so this is one thing. And second is that so far I discussed mostly admissible level, but just because we know how to do, but non-admissible level are also very interesting. And appears in Argyras Douglas theory. And so here we have some very few examples and conjecture, and I finish with that. So, okay, so using different methods, we can discuss also some non-admissible collapsing level. So in fact, we can do it when we know explicit OPEs. So for instance, in small rank, in B2 and G2, my student Justin Factel did the whole computation of OPEs in rank 2, and from this, they observed with Adamovich some nice isomorphism. So we have this one for B2. We have another one which is not exactly collapsing, but it is an isomorphism between non-trivial W algebras. And the last one is a collapsing one. The last one is very interesting because the last one should imply that the associated variety of L-2 of G2 is just a closure of the subregular one, which is something conjecture before. The reason is that, as it is well known, G2 can be obtained as the S3 action of the S3 invariant of D4 using the outer automorphism of the Dynkin diagram. And on the other hand, our result with Arakawa shows that the associated variety of L-2D4 is a minimal nilpotent orbit. Also, it is known that the projection map from D4 to G2 is exactly the subregular one of G2, if you project the minimal one. So this suggests that the orbifold of L minus 2 D4 through the action of S3 is exactly L minus 2 of G2, and that the associated variety of the orbifold in this case is exactly the orbifold of associated varieties. So anyway, this collapsing level, it's also interesting for other topics. And lastly, we formulate a number of conjectures for non-admissible results coming from geometry and asymptotic behavior of characters, but it's not exactly true because our results are not true for non-admissible level. But recently, with Thomas Crutchis and Arakawa, have an idea to solve at least the first conjecture, and we check these days that at least the first one is not anymore a conjecture. So, but we don't have general theory so far to study non-admissible levels. Okay, I think I stop with these conjectures.
Thanks so much for the lovely talk. Maybe we'll. And I see a question from Oswin. Go ahead.
Hi, yeah, so I had a question about, some nilpotent orbits have symplectic resolutions while others don't. Does this translate to some property of the corresponding VOA?
Yeah, that's right. Nilpotent orbit closure, the normalization of nilpotent orbit closure always have symplectic, are always symplectic. So in our cases, it's not true that all nilpotent orbit closures are normal. So for instance, in G2, they all appear as associated varieties, but one of them is not normal. So I don't know what is your question, how it is interpreted in our story?
Oh, no, my question is, so even say the minimal nilpotent orbit in type A, it has a symplectic resolution, but in other types, it does not. I was wondering if this geometric property translates to some property of the corresponding VOA.
So far, we haven't really used that. Translate, you mean a kind of resolution for vertex algebras?
Yeah, what does that mean? Yeah.
Yes, that's very interesting. So far, we haven't really explored this in this term.
Okay, thank you.
Okay, but as I said, okay.
Thank you. Are there other questions? I see a question from Jethro.
Hi. Hi there.
Hi.
Yeah, it's just a question about the definition of quasi-Lis. So you know the condition on finitely many symplectic leaves implies that the zeroth Poisson homology of the C2 algebra is finite dimensional, right? Do you happen to know if the converse is true, or if there are counterexamples?
Okay, so concretely, you take RV divided by the bracket space by whether this is finite implies that finite dimensional implies that there are finitely many symplectic leaves. That's an interesting question.
So I think a priori it's weaker, and I think it's enough to prove the modularity theorem.
I think it's weaker, but maybe I should have a look in the proof of Ettinghoff and Schedler to see what is. Yeah, I have never tried to see the converse.
Okay, yeah. Thanks.
Are there any more questions? I can't quite ask a question, but I have a vague thought. So these Slodowy slices of nilpotent orbits were important in work I was doing with Davide Gaiotto a number of years ago, which...
Sorry?
Well, I don't have a good question, but I just have a comment, which is that these Slodowy slices of nilpotent orbits were important a number of years ago in work I did with Davide Gaiotto involving certain configurations of branes and supersymmetric configurations. I think there must be a connection somehow.
Thank you.
Fair enough, I want to ask a sensible question. There might be, okay. So it's just a stray remark, which I can't.
Okay, thank you so much.
Are there any more questions? In that case, we'll thank Anne and C, well, both of you really for wonderful talks this morning. And I guess the afternoon session, we take a break of about an hour or so before the afternoon session. Maybe it's an hour and a half. The afternoon session starts at 1 in Brazil.
Yeah, it's an hour and a half from now.
Okay. So see you all, or many of you, for the afternoon. Thank you.
Thank you very much.